Okay, so welcome back. Our next speaker is Professor Chen. He's going to tell us about reflected entropy and its implication in AdS3 WCFT.
So thanks for the introduction, nice introduction. And so first of all, I would like to thank the organizer of this wonderful conference to give me the opportunity to introduce our recent work on reflected entropy. So the talk is based on several papers with my former postdoc, Clement and Boyan, and the other two graduate students. Both of them have graduated, and Chen and Yue-Feng Liu. And so I think this talk is quite related to the former talk by Professor Chern-Simons and on the we'll see on the entanglement wedge cross-section. And so let me start. And so we know that in the past for more than 50 years, one of the most important developments in AdS correspondence is the introduction of the entanglement in the playground. And it has now it has widely believed that the quantum entanglement may play a fundamental role in the emergence of space-time and also the gravitational dynamics. And since the work by Liu and Takagi in 2006, and so before that, let me just give a brief review of entanglement entropy and its holographic computation. And I think some of this has been, I believe, has been talked about by Chen. And so let me just brief review. So this is the standard definition of entanglement entropy. So it's a quite important notion in quantum world. And so in the simplest case, we can divide a whole system into two parts. So this so-called the bipartite system. And such that the total Hilbert space of the system can be written as a tensor product of the Hilbert space on A and Hilbert on B. And for a wave function in the whole system, we can define a density matrix like this. And after we tracing over all the degree of freedom in subsystem B, then we get a reduced density matrix like this, rho A. And then we can define entanglement entropy as the von Neumann entropy of this reduced density matrix. So this is the basic definition. So physically, we can understand this entanglement entropy as follows. It's the entropy of our observer, which can only accessible to A, but not to B. And also one understand as the entanglement entropy as some kind of the quantum correlation between A and B. So this is the basic definition. Let me give a simple example. So for a simplest case, it's a two-spin system. And in this case, if the wave function for the state of the system is just a product state, then we know that there's no entanglement between A and B. But if the state is an entangled state, or the EPR state, it takes this kind of form, then the entanglement entropy is actually it's take the maximum value, it's log 2. And so this is the basic definition. And this is so we say that in order to compute the entanglement entropy, one has to do from definition, we have to start from the density matrix of the whole system, then tracing over some degree of freedom to get a reduced density matrix, and then we define as a von Neumann entropy to get entanglement entropy. So it becomes more and more complicated if you have more and more degree of freedom in the system. So if we consider a quantum field theory, it becomes very complicated. And the basic idea is that the vacuum in a quantum field theory is highly encountable. So in this case, we can consider a quantum field theory defined in a d+1 dimension. So with one spatial directing and d-dimensional spatial manifold. And then the subsystem in this case is defined at a time slice. Then it's a submanifold of M of this spatial manifold. And this has been, in this case, the entanglement entropy has first started in the middle of 1980s. And it's a very interesting topic and has been one of the most important property of entanglement in quantum field theory that it satisfies some kind of the error law. That means the leading term in the entanglement entropy, it's proportional to the boundary, the error of the boundary of A, and also some subleading term. And here this epsilon is a UV cutoff. And gamma is some kind of is a constant depending on the dynamics of your system. And this formula suggests that the entanglement between two subsystems, A and its complement, occurs at the boundary most strongly. And a simple physical picture that you can take around the boundary. You have the two sides of the boundary. You have a pair production around the boundary. So you have the correlation between the degree of freedom between the two sides of the boundary. But it's very difficult to compute even for free field theory. So I think this has been discussed carefully in this century. And so actually I have to emphasize that in this story it's much more interesting and somehow it's quite related to the von Neumann algebra in operator algebra. So strictly speaking, the entanglement entropy in this case is not a well-defined notion in quantum field theory because that the algebra of the observables in quantum field theory is formed as type 3 von Neumann algebra. That means one cannot define the density matrix in this case. So, we cannot define the entanglement entropy in this case. But we can define some other entanglement quantity, like the relative entropy, that is well defined. So this has been emphasized by Edward Witt a few years ago, but the original work has been known in 1960s. And okay, we can ignore this caveat since we can consider quantum field theory. We can describe that. So it's not just a continuous system. If we describe a quantum field theory, then the discussion before can be well defined. Okay. And so, as I mentioned, it's very difficult to compute the entanglement entropy. But in the case when this quantum field theory had a holographic view, had a gravity view, then Liu and Takagi gave a nice prescription. And so as shown in this figure. So this is at the boundary quantum field theory. We want to compute the entanglement between A and B. Then the entanglement entropy now, in this case, if the view for gravity, just Einstein gravity, then one can find a minimal surface, which is homogeneous to A. And then the entanglement entropy, now the holographic entanglement entropy, now it's captured by this formula. So you see that it's proportional to the area of this minimal surface, and also its form, it's reminiscent of the black hole entropy. Actually, Newkowitz and Madsen has shown that holographic entanglement entropy can be taken as a generalized gravitational entropy. Yeah, it's even though there's no U1 translation symmetry, but for Einstein gravity, one can show that it's exactly a kind of generalized gravitational entropy. So this formula is called RT formula. It has played very important role in the very recent development in holography. So I have no time to review the various developments in this area. So today, my topic is to not focus on the holographic entanglement entropy, even though it's closely related to it. And so, as I mentioned, even though the study on the entanglement entropy has led to many insights into the holography, it's necessary to investigate other quantum information quantities, which may shed new light on holography. For example, natural ring entropy, relative entropy, complexity, etc. And for example, for the ring entropy, in this case, it's not just a simple minimal surface in the bark. You will see that for the ring entropy case, the bark background cannot be neglected. Then in that case, one has to solve in the bark side, one has to solve to find the gravitational configuration carefully. Also, we know that entanglement entropy is defined as a von Neumann entropy of a reduced density matrix. For von Neumann entropy, for entanglement entropy, it's a very nice quantity to capture the quantum correlation between subsystems, but only for the bipartite pure state. For other cases, for the mixed state, for this multi-partite state, it's not a proper entanglement measure. So that's why we have to consider other quantum information quantities. And so the question is that there's some other quantum, other entanglement measure and its and their holographic view. So this is a very interesting question to ask. And yes, and the answer is yes. And there has been in quantum information in error, there are some measure, other entanglement measure, like the logarithmic negativity or entropy to capture the entanglement in the mixed state or this multi-partite state. And very recently, in a few years ago, the people in AdS community proposed this so-called WCFT entropy. So that's the focus of my talk. And this quantity, this notion originates from the study of the entanglement of purification. So before that, I have to introduce some notion in holographic entanglement. This is the so-called entanglement wedge, and it's defined to be the bark, a domain of dependence of a four-dimensional one surface. So it's this four-dimensional one surface is interpolating between the boundary of this subregion and its holographic entanglement surface. So in this figure 8, it's easy to understand. So we say that this is a 1+1 case. So we say that this is the subsystem A. So it's just a simple interval. And this arc, it's RT surface. Now it's a geodesic in the bark. So and the form a four-dimensional one surface. And we try to, in the bark, so it's in 2+1 dimension. We try to find its a domain of dependence. Then we get this kind of the figure. And in figure B, it's for the two interval case, and actually, it's when these two intervals quite large and close to each other, then we get this kind of form. In this case, we know that the artificial surface, it's not this one or this one. Since we try to find a minimal surface, there's a phase transition. So we have to, actually the artificial surface is this one, this small arc, and this large arc. And then we get this. So the domain of the dependence is this kind of form. And this is so-called the entanglement wedge. You see that it's in the bark, it's a four-dimensional surface, and it's and we try to find its domain of dependence. And entanglement purification means that we start from a mixed state, we try to purify it. And there's a various way to purify it. We can combine it with an auxiliary system, such that the combined system, the total system is in a pure state. And there's a various kind of the purification. The entanglement of purification is defined to be the minimum, the one with the minimum entanglement in the purification. And so you see that since we have various kind of the purification, so it's generically it's hard to compute. And it was proposed by these two groups that phonographically the entanglement of purification is related to the entanglement wedge cross-section. And what's this? It's a minimal area surface in the bark that divides the entanglement wedge of two disconnected intervals. So let me give an example. So we say that this is the okay. Now we are working in the global patch and our AdS, and we have this. So the boundary is this red circle, and so actually we have this A and B and the complement. So this figure is just simple at the time slice, and not the whole system. And we say that we try to since we're tracing over this the degree of freedom in this arc and this arc, then A and B now it's in a mixed state, and the purification. Then we try to compute the entanglement of purification, and holographically we'll say that since A and B are quite large, and we say that the entanglement wedge it's in this white corner. And now the minimal surface, minimal area surface entanglement cross-section is this EWCS, this blue line. It's divided into two parts. So and that is the and we try to find you see there are many ways to divide these two parts. But the minimal one is this one, this blue one, this blue line, and the straight blue line. Then it's the minimal area surface. So that's the entanglement wedge cross-section in AdS case, and this is the so these two groups propose that entanglement of purification of A and B is captured by this entanglement cross-section EWCS, and the question is that there's some other kind of quantum information. Since we know that in field theory we don't, it's quite, as I mentioned, it's hard to compute the entanglement of purification in field theory side. Then there could be a question that if there's some other quantum information method also correspond to this EWCS. Also, there are some candidates like the logarithmic negativity, odd entropy, and Lifshitz entropy. So, what's the Lifshitz entropy? So, Lifshitz entropy was proposed more than 4 years ago by Duta and Fortler, and it's defined as for A and B, for this bipartite quantum system, it's Lifshitz entropy in a mixed state. It's defined as this as the first we do some kind of this called the canonical purification of mixed state. That is maybe the most easily understood purification, so-called the canonical purification. And so we simply double the Hilbert space. So originally we have the Hilbert, the tensor product of the Hilbert A and B. But now we double the whole Hilbert space at HA, HA prime, HB prime. And now in this doubled Hilbert space, we have a pure state. Then we trace over the degree of freedom of B and B prime. Then we get a reduced density matrix of A and A prime. Then for this reduced density matrix, we can define its von Neumann entropy and also the range state entropy. Okay, so this is the very similar to the Euro entanglement entropy, but now we have to do this the so-called canonical purification in a doubled Hilbert space. And some nice property of this entropy, for example, if the AB itself is a pure state, we say that this A, the entropy between A and B is the entanglement of SA, 2 times SA or 2 times SB. And for factorized state, we know that this SA equal to 0, so this is this entropy also get 0. And one can prove that the entropy is bounded between the mutual information between A and B and the 2 times the minimum of SA and SB. And from this inequality, one can define so-called the Markov gap between the entropy and the mutual information. And for a non-vanishing Markov gap, that means for a contiguous subsystem ABC, that means a signal's irreducible tripartite entanglement, and it's beyond the bipartite entanglement and the GHZ type entanglement. And also there's some other inequality for this entropy. And the physical implication of this entropy is that it may serve as a probe of tripartite entanglement, as I mentioned in the last slide, and also it characterizes the refined topological order. So we will see it. And it has been studied in various systems, like in the random tensor networks for free scalar, free fermion, and in Chen-Simons theory, and in Lifshitz theory, and also it's one can take it a new pole of holography. So I will introduce our work in Chen-Simons theory, Lifshitz theory, and in holography. Okay. In field theory, so just like the entanglement, to compute the entanglement entropy in field theory, one can apply this so-called replica trick. But for the field entropy, one has to do so-called double replication. That means we try to make not n copies of original theory, but n times m copies of original theory. So the first step is the replication is to replace the canonical purified state by its m copies. So it's this rho AB square root. It's the original density matrix, reduced density matrix. Then we make m copies of it, and then this state can be described by path interval. And the second replication is to compute. Now it's not, since we have a double replication, so it's not nth ring entropy. So we call it the mn ring entropy for a positive entity. And we try to compute this quantity. The next step, we try to trace over the degree of freedom in B and B prime. Then we get this kind of quantity. From this one, from this psi m, we define as rho ABM. Then we trace over the BB prime, we get a reduced density matrix in AA prime. And now it's we get this to read this n ring entropy depending on m and n. So the final step is to, we have to believe in an analytic continuation to take n and n to 1. Okay, to n and m to 1 to read this density. Okay, this is some other way to use this partition function unnormalized and its normalization. So finally, you get this kind of formula. So the essential part is this formula. This is a figure to show how to do the application. You see that it is in M original system, and you have to make n copies of it. Yeah, I don't want to go to the details. So first, let me introduce our work in Chen-Simons theory. Now, we know that in Chen-Simons theory, the topological entanglement entropy, it encodes the information about the topological order for ground state of gap system. So this is the entanglement entropy. Now, important part, this is the first part is the error law, and second part is a universal part. It's depending on the total quantum dimension of the system. And it's only a good entanglement measure for pure state and of part-type entanglement. And we studied the entropy in 2+1 dimensional Chen-Simons theory and determined what topological data is encoded. And actually, more precisely, we focus on this kind of figure, this kind of configuration. This is on a sphere, this is on a torus, and we know there are three non-overlapping regions A, B, C. So after we tracing over a division C, we get a mixed state and a mixed state of A and B. So same on the torus case. Now, for this kind of configuration, the Euro entanglement structure of such state has been investigated in terms of the logarithmic negativity and the mutual information. It has been well studied in the literature by several groups, Weinfeld and Vedal, long time ago. And we studied this entropy in this configuration and using two different approaches. That is a standard in computing the entanglement in the Chen-Simons theory. One is the AdS theory, and the other is the surgery technique. And both approaches are leading to the agreement, the complete agreement. And the main result is that finally we say that the entropy in this setup, the A and B, the entropy between A and B exactly is the mutual information between A and B. That means the Markov gap in this case is simply vanished. Even though if one considers the ring version, they do not agree in general. But after you take the limit n and m tends to 1, you will say that you will get this relation. And this is not the whole story. Quite last year, you and his collaborate, they addressed this issue, but in a different configuration. And since that, they have a very nice, insight that they find that the entropy can be a refined topological order. And that means, so as I mentioned before, this quantum dimension B, not it's a universal contribution. But this quantity cannot distinguish the abelian order from the non-abelian order. Since you say that there are different topological order, but they may have the same total quantum dimension. And so they try to define more refined topological world. So consider this kind of configuration like A and B. And in figure A case, notice that the logarithmic negativity distinguishes the abelian and non-abelian. But for the figure B case, you find that the Markov gap will not vanish, and there's a distinct universal contribution to the return. So the work, I think, is quite important. And the second project, in our second project, we try to answer the question that if the return entropy is a good coordination measure or not. And so we know that for a tripartite density operator, there should be this kind of relation. This dot is a kind of coordination measure. Yeah, we don't know what it is, but intuitively we should expect that the coordination between A and B and C, so the union of B and C, should be larger than the coordination between A and B. Since we say that the system B, the union of B and C shrink to B, so that means the coordination measure should be also decrease. That is called the monotonically decreasing property, and under the partial trace. So the question is that is the reflected entropy also monotonically decreasing under partial trace? And it has been proved in the original paper that if n is greater than 2, not less than 2, then the reflected ring entropy is monotonic. And also it's true. I mean in any case, it's true for holographic state. The monotonicity also true for holographic state as a consequence of the entanglement wedge nesting property. And it has been proved to be true for free scaling. But interestingly, last year it was found that for a certain quantum system, is by some kind of tensor quantum state in a kind of a very simple setup, the monotonicity of the return entropy gets lost in this region when n is smaller than 2. So then it's an open question if the this monotonicity of the return entropy in quantum field theory, it's not certain. And we try to answer this question in a free Lifshitz theory. And the Lifshitz theory is a certain class of the non-relativistic quantum field theory, and whose ground state wave function take a local form. And we consider a non-compact Z equal 2 Lifshitz critical boson and its massive deformation described by this Hamiltonian. And now we write written in this canonical conjugate to this to phi, and omega is its mass. So in the critical case, massless case, omega equal to 0. Then the theory is invariant under this Lifshitz scaling with critical exponent equal to in this kind of restraining, and the classical action that of a free non-relativistic particle. And the key point that in this case for this critical boson and its massive deformation, why we can compute the entanglement entropy exactly is because that in this for this kind of theory, the ground state can be expressed in terms of a path integral or of a one-dimensional leading theory. So originally we are working in 1 + 1 dimension, but the wave function can be written. The ground state wave function can be written in terms of a path integral of a one-dimensional leading theory, and it's a free series. So that's why we can compute. And now, for example, for the density matrix corresponding to the ground state can be written in this way. And sure, we have to impose some kind of boundary condition on the full system, like initial boundary condition, Newman boundary condition, or theoretical boundary condition. But it's not important, not essential to keep which kind of boundary condition. So in order to compute the entropy, we have to start from three non-overlapping subsystems A, B, C, and we get this kind of reduced dimension matrix approaching over the degree of freedom in C. And we computed the entropy for two intervals, either adjacent or disjoint, and we obtained explicit formula for general range indices. And so this is the result. And so this is now we consider the two adjacent regions, A and B, and its complement. And we found that the entropy is not monotonic on the partial trace. And it's providing the first counterexample to monotonicity in free theory. So we see that in this right figure. And the monotonicity actually can be read from this quantity. And the V it's the length of L, the ratio of LB and LA. So that means some kind of if we shrink the A will the length of A will B, then we get some kind of partial trace. We see that the quantum coordination, the variation of the quantum coordination. We see that for this it's negative. We see that when n it's smaller than 4 over 3, and it's negative in this area. This is a numerical study for general omega. But for the critical case, when omega equal to 0, actually we can do some analytical computation. So the final result is take this kind of form. And so for n smaller than 1 or n equal 1, it's negative. And when it's greater than 1 case, we say that we have this numerator. So that means this numerator shows that when n equal is smaller than 4 over 3, it's negative as well. And it's positive for n is greater than 4 over 3. So that means the monotonicity, in this case, in the Lifshitz scalar case, it's broken. And so our result provides a first example to show that the entropy is not a good quantum measure in field theory. And so the last topic of my talk is on the entropy and its implication in holography. And so in a standard AdS correspondence, we know that from its definition and a simple computation, one can understand that since we have doing the canonical purification. So you see that we have A and A prime, B and B prime. And also this entanglement with cross-section also get double. So the entropy between A and B, so it's 2 times of the error of the entanglement wedge cross-section over 4Gn. So, and also there are some other subleading terms. So our motivation is to understand if we can use the entropy as a new probe to study the holography beyond AdS-CFT. And for example, in AdS WCFT for flat holography. So for the flat holography, the question is quite subtle and we have no certain answer. For the AdS warp safety case, we have a quite concrete result. So let me first introduce a little bit AdS warp safety. So we know that in modern understanding, the semi-classical AdS gravity and its holographic field, it's very sensitive to the asymptotic boundary condition. For example, for the standard Brown-Handel boundary condition, we can't read, we can't find this AdS standard semi-classical AdS safety field. But there's some other consistent boundary conditions proposed by Wilson and Andy and Geoffrey Champari. And they found another set of the consistent boundary conditions. So now it's called the CSS boundary condition. And this leads to AdS3 warp safety too. And so simply speaking, so under this kind of CSS boundary condition, the AdS3 gravity or semi-classical AdS3 gravity could be due to a holographic warped safety. And this warped safety has a symmetry group generated by Virasora-Katsmudi algebra. And holography in AdS warp safety has been studied by Wilson's group quite carefully. And the proposed so-called the swing surface proposal is different from the RT formula. So in RT formula, you get a minimal surface, but now it's not a simple minimal surface. This is a figure, and so this is a boundary, it's a warp safety, you have an interval A, but it's holographic entanglement actually is captured by like a swing. So you have a two row and a bench, and so this is a null line, gamma plus and gamma minus. And between gamma plus and gamma minus, you will try to find that bench with a minimum minimum length, and this gives you the so-called swing surface proposal. And but it's not very clear since we in this case it's quite subtle since the infused side it's not a standard Riemann geometry, Riemann surface. It's strictly speaking, it's a Newton-Cardan geometry, and so the entanglement wedge it's not very clear. I think in the original paper we called the pre-entanglement wedge. And also there's some other questions. How about the gravity side and how to read the semi-classical acting in the gravity side? It's not certain also. And so that's why we try to use this entropy to give some new side, to try to share some new side of AdS warp safety. And the computation is it's quite complicated. I think I have no time to explain very clear, in very detail. And so in Euro case, in Euro safety case, and we know that to compute the ring entropy, there are two different ways. One way is to compute the partition function of our original safety, but on a very complicated Riemann surface. And since you have a replica manifold, so it's a partition function in a replicated manifold. There are some other way. The other way is compute the coordination function of traceable operator in the orbifold safety. But now the orbifold safety in the for the ring entropy is a non-abelian orbifold. So that makes things very complicated. So this is some technical detail I just skip. And so you finally see that the ring entropy in any dimension, you see that it's a kind of coordination. But now coordination function of the twist operator. This is the twist operator in higher dimensions non-local, and for B and for A, this is a two twist operator, and it's defined in this in an orbital CFT. And the dominant is some normalization factor. And in two-dimensional case, we know that the twist operator is a local operator. Then the local operator as the boundary of the interval. So that is a point operator. And it's sigma and sigma minus. You can take it as sigma tier. And this is for A, this is for B. And the essential part is to work out the conformal dimension of twist operator and also the OPEs. Since you have a T-channel or 4-point function, you have to using the conformal symmetry. Once you know the conformal dimension of the twist operator, and also you take the for the holographic CFT, you can take the Knox limit, and then since the vacuum block is dominant, and then in that case you can compute this coordination function step by step. But for the warp CFT, there are some other complicated. And we know that the transformation is different. For the warp conformal transformation, you have two directions, X and Y. But X is a Euro diffeomorphism. But the transformation on Y is slightly different. Yeah, you say that it's Y prime equal to Y plus GX, depending on the X. So, and F and GX are two arbitrary functions. So that means you have one can work out the node currents P and P and transform like this way, and some technical detail. And now, since it's the symmetry group is generated by the Virasoro and Kac-Moody algebra. So this TX is generated the Virasoro algebra, and the P generates the Kac-Moody algebra. So now you have a parameter K. It's a Kac level, U1 Kac level. And now you see that this is the algebra of Virasoro algebra and the Kac-Moody algebra. And the first line is Virasoro algebra, and also U1 Kac-Moody algebra, and also between L and P, the commutation relation. And now the twist operator. We try to work out the conformal dimension of twist operator in this non-abelian orbital warp CFT. So let me just introduce the basic idea. This kind of the twist operator are primary operator, but in our warp CFT, the property are characterized by the conformal dimension and also this U1 and the U1 charge. But now it's compared with the case in Euro CFT. Now the discussion are more subtle, the philosophy is very similar to the case in the Euro CFT. One can compute the stress tensor T in a reflective manifold. Then you can use the uniformization map of this from this replica manifold to a sphere, to a topological triple sphere, and since this stress tensor you have, under this kind of the conformal transformation, it has some short derivative, etc. Then you say that it gives some non-vanishing answer on the left-hand side. On the right-hand side, one can use the Ward identity. This is a two-point function with this stress tensor, and it gives you some kind of the Ward identity. But now it's in a trivial manifold, CP. And with this Ward identity, compare two sides, one can read out the dimension and also the charge of the twist operator. So that's the very similar. Actually, it's very similar to the case in Euro 30. But now there's some subtlety. In the warped case, first of all, the uniformization map is different from the Euro safety case. In the Euro safety case, we know that it's a holomorphic coordinate and anti-holomorphic coordinate. So they are complex conjugates to each other. But now X and Y are quite different in the warped safety case. So for X, it's some kind of the uniformization map, but for Y, it's quite different. And also, there's some quite subtle issue on this spectral flow and etc. For example, when you do some kind of the uniformization map under this monodromy transformation of X, you see that the Y direction gets shifted, gets translated, and so you here there's there's a small interval, and another rotation get another one, and this quantity and this translation is closely related to the conformal transformation I mentioned before, and to do the computation, one has to, I think, to make things simple, I just tell you the basic idea. The philosophy is that we try to keep the charge conservation in the whole transformation, various kind of transformation. And these allow us to read the conformal dimension and the charge of the twist operator. And for example, for the entropy, you can read the conformal weight of the sigma GA, sigma GP like this, and the charge. And the anti-twist case is this kind of form, and also the kind of the OP between GA minus 1 and GB. And this allow us to compute the a 4-point function of the twist operator. And now this is the this is the 4-point function. And in the safety case, we only care about the T-channel expansion, which is equivalent to take the limit of the cross ratio x to 1. And also we have to make an assumption that even for the holographic warp safety case, in the not same limit, only a single block is dominated, and the vacuum block is dominated. So that allows us to get this kind of answer. So this capital D, this part. So we see that in the computation we have this is the dominated part, numerator part, and there's a dominated part. And this part gets cancelled between the numerator and the denominator in evaluating the eccentric entropy. So, and finally, you will see that in the warp safety case, the holographic warp safety case, the entropy of A and B is only 1/2 of the A and B in CFT. And so even though the computation is quite complicated, you have to for the entropy case, you have to decide the boundary condition of the twist operator. What kind of for different twist operator, you have the different conformal weight. But the final answer is quite simple. And on the holographic side, so it's we use this 3-surface proposal. So as I have mentioned before, and now you have two. Now we have the two intervals, this AB and CB. And so for each case, since there are two the AB and CB are close to each other, so we say that the holographically we find actually it's the swing surface of B and C, and you get this now. Now this is the bench, and for A and B we get another part. This is the loop, and this is a bench. And now entanglement surface, entanglement wedge cross-section is you try to find the minimal or the interval of the minimal length between these two benches. So that gives you the entanglement wedge cross-section in this case. And I think 1 minute. Yeah. Okay. Yeah. And okay, this is some technical detail. You can work step by step. And finally, you will see that it's not not very complicated. One can work on just step by step. And finally, you will see that in this case, entanglement wedge cross-section takes this kind of form. Also, it's only 1/2 of this. I think maybe that's a typo here, and only also it's 1/2 of the euro for the holographic due in safety case. So sorry, this is the field theory computation. This one, so it's not a typo. This field theory computation I mentioned before, but since even though we worked in a vacuum in the vacuum state, we can do a kind of the transformation for a thermal state. So that allows us to read this quantity, and so you see that it's 2 times the entanglement wedge cross-section on the back side. So let me conclude, and we computed the topological reflexivity in our first work of certain state in 3-dimensional Chen-Simons series, and found that the Markov gap is simply vanished in all setups for the configuration we consider. And we investigate the reflexivity in 2-dimensional free-Lifshitz scalar series, and found that the monotonicity is broken in this case. And we developed the technique to compute the dimension and charge of various twist operators in non-abelian orbital WCFT, which allow us to read the reflexivity, logarithmic negativity, and order entropy. I didn't mention these 2 quantities, but in our work, we can also compute these 2 quantities. Very similar to the reflexivity. The difference only the property of the twist operator. And compared to the back computation, and so that means we study the reflexivity in the context of AdS3 WCFT2. But then we find this formula. But now it's the pre-entanglement wedge cross-section in this case. And it's the final answer is it's similar to the result in the Euro AdS3 WCFT2, even though the technical it's very different and quite complicated. And this formula provides a non-trivial support to this swing surface proposal of holographic entanglement in AdS3 WCFT2. Okay, thank you.
Talk, questions?
The flat case.
Slide holography. Yeah, we have. I think somehow it's not hard to Indian group also study the reflexivity in the flat holography, but somehow it's we have no very clear relation between the back side. So as you know, we have discussed before. But for the field theory side, since it has been computed by some other group, so we didn't publish the result. Yue Feng had a separated paper, but it's a non-paper. the three give many comments and suggestions to that manuscript. Yeah, I don't think it's since for me it's not very clear on the backside. So,
Right topography, I mean, a similar interwedge cross section, which is a minimal surface connecting two RT surfaces, and they get.
yeah.
I was referring of the paper written by the Indian group. So, no, no. That reference is not anonymous. So it's, but the calculations matches quite well. So I don't quite understand what you mean by the bucket picture is not very clear. Because if you do the saddle point of the geodesic that connecting two RT surfaces of intervals, they exactly matches to their field theory calculations.
Yeah, I think the yeah, in the flight global, it's yeah, somehow it's not clear to me. The technical detail, the mathematics is not very difficult, you know. Yeah.
So I just have one comment on the refractive entropy.
Uh-huh.
Since there's so many counter examples that this refractive is not monotonic under inclusion.
Mm-hmm.
So I feel that as you said, that even in the field theory side, for Lifshitz scalar theory, you already found that the monotonic property is violated under inclusion. So I guess maybe there's not so much motivation to study this quantity
Anymore, right?
any further.
Yeah.
Any other questions, comments? If not, let's thank the speaker again.
Okay, thank you.